All right. Hey everyone. Welcome to week 7 applied track. Today we're going to talk about improving your ML models. As always, the asset cluster is in the link, and our attendance code today is get good. Some skill issues going around. But I don't know. What? Oh, okay. That's quite ironic. I will. Okay, I'm. I'll let Jordan know when he comes in. But I don't think there's anything I can do about that, right? Yeah. All right. Anyway, so we're just gonna be talking about various techniques that you can use to improve your ML models, some regularization techniques and whatnot. So first, some announcements. We have obviously the asset cluster is updated, as you can check it out at the link. Also, next week we have a theory track where Venkat is going to be talking about ensembles and differential privacy. So that's at 6 p.m. next Monday at Kaplan A65. And finally, we have, and this is our roadmap for theory track. And as you see here, week 8, ensembles and epsilon DP privacy. And then the last week, we're going to be talking about deep generative models and modern deep learning. So without further ado, let's talk about some of the techniques. So one of them is transfer learning. So transfer learning, how many of you have heard of transfer learning before? No? Okay. So one problem you might have if you have a relatively niche task is that you might not have a lot of data. So that makes it difficult to kind of train a model effectively. But there's a trick. You can find a related task. So basically, we need a lot of data, boatloads, container ships loads of data, but we don't have it. So what do? All we do is we just take a related task and say, oh, we trained the model on this related task. It can probably classify, it can probably do our task fairly well as well. So basically, like this, if Alice can drive a car and Bob can't, who can learn more quickly how to drive a tractor? Probably Alice, right? Because, car, tractor, they're different, but they're close enough. So as far as how this actually is implemented, so we have model A, we call it the pre-trained model. And then what we do is we replace the block layers here, or these layers at the end, and we put them in, and we call that model B. Once we, so it's similar, but it's different with different layers at the end. And then we fix the front layers, the part that is still from A, and then we only train the part that's B. And so, and here also you have a bit of pseudocode, some PyTorch, what's some, it's right there.
So just to emphasize what Ray was saying, this is like the really important technique that we use in the machine learning model. We take models that are already not trained before, that already been trained on all these data. It's like take their base. There's literally no way to
right.
So that's what we're doing. And the reason why we freeze the models weights beforehand is because we don't want to affect already trained weights too much, because if we do, that might lead some unwanted consequences. So we leave the weights. It's your choice at the end of the day. When we freeze them, we'll lower the learning rates for the weights that we compare.
Yeah, basically the part that is generalized, we don't touch it. We just keep it there, and we leave it. And we only train the part that's specialized to our task. So another technique that you can use. Hello, Jackson. All right. So The second part is learning rate scheduling. This is basically a way of changing the learning rate according to some schedule. So there are various, so quick recap on learning rate. If you have a low learning rate, it's going to be very, very slow to go down. And if you have a high learning rate, it could just shoot past where you want it to go. So both of those are not good. So instead what you want is somewhere in the middle. Basically, you want to be able to approach your minimum fast enough, but not too fast as to overshoot it. So one of the ways we can do that is we can schedule changes in the learning rate between epochs. And so we can just change it as appropriate. So in this example here, we start with 0.1, then go to 0.05, then go to 0.025, and so on and so forth as we keep going through the epochs. So here are just some examples of learning rate schedules. So we have constant, time-based, exponential, linear, and step-based. So step-based, we just do it on at certain steps, and then the other ones are kind of implied by the name. And then here's a graph of how they actually do. So we can see that constant and time-based are, at least in this graph, they perform the best. Step and exponential, they tend to, as you see there, they tend to get a little bit less accuracy. They still do well, but not as well as the other schedules. And so when we talk about ResNets, this is how they're trained. So as we see here, they use a learning rate scheduling. So as you see, it's a step kind of process where at like 15 and 30, they take significant steps down. But beyond that, it's more of a, looks like either an exponential or time-based. Yeah, which it's one of those two. Basically, yeah. And then now we get to a thing called Nesterov momentum. This is totally not whatever. I was gonna say something else. Gradient descent only works. So the problem with gradient descent is it only looks at the current location and nothing else. So we look at how the gradient. So instead, what we want to do is we want to look at how the gradient has been performing so far and use that to inform our decision. So what we do is we keep sort of a running mean of the gradient so far, and we do it in a thing called momentum. And so what we'll do is we'll set v equal to 0 initially. That's our momentum kind of variable. And then we have alpha, which is a parameter between 0 and 1. We typically set it to like 0.9 or 0.99. Then until the stopping criterion is met, we compute the gradient. We're going to update it according to this rule. So we're going to do our scale. So V, we have alpha times V, and then we subtract epsilon, which is the learning rate, and the gradient G. And then finally for the gradient step, we update theta. So we say theta is now theta plus V. So if just I have to say it, if y'all go on to take EC 147, you're actually going to learn more about this. So I just found. Okay, yeah, it's fine. I'm good. Sorry, I thought you were mad at me. Okay. Anyway, momentum does have its inefficiencies though. So it tends to overshoot minima. So if you imagine a ball rolling downhill, it'll just go down, but it'll come back up. So that can happen if we if we just leave the momentum formula as is, but we can change our momentum formula. We can calculate where the momentum wants to take us and then calculate our gradient. So it's similar to normal momentum some of the time, because the gradient isn't changing very quickly, stepping forward doesn't have a major effect, but we perform better when we approach a minima. So momentum just overshoots, whereas with Nesterov, we're able to preempt some of the overshooting. So we're able to see, we're able to kind of predict it in advance. So here's our Nesterov momentum. This is just regular momentum. And then for Nesterov, we actually compute the gradient in the alpha v direction. So we compute it at this new point, and then we say, okay, so we update according to this rule. Basically, this is just a fancy math way of writing it, as they say. So really the biggest thing to remember is that Nesterov just allows you to predict kind of what's going to happen. It allows you to adapt to where you want to go, and that'll help you avoid overshooting. So we also have examples of what we talked about a lot in a lot of the notebooks in this cluster, and that's the demo. I'll get back to you about the code. I don't know what the deal is, but now thank you guys. Yeah. Okay.
What is J?
J is the gradient, or J is the cost function. Yeah. What's its own? Yeah.
So essentially, what
Yeah,
we're doing here
yeah.
is not that different from normal momentum, right? If you look up here, we're just using G in the place of the gradient instead, right? Because as you may be aware, this is just this is very similar to gradient descent, where we're taking the gradient. The idea with the momentum is that we are over time taking like a localized picture of what the gradient has been like. So that way, like we talk about, like if your gradient has been going down like a lot, and then all of a sudden it's telling you to go like this way, instead of completely turning that way, it might be a good idea to keep going down just in case that that's like a small bump in the loss landscape, and here, the only difference between this and this in regards to the gradient is the gradient there is just the current parameters, right? And then here, what the gradient we're taking of is what direction is going to improve our loss the best for not our current parameters, but how we think we are going to update our current parameters, it's sort of like giving us the ability to just look a little bit into the future and think about, okay, if that's what I think I might want to do, how is that actually going to affect things, and then update based off of that. So it is a little math heavy. If you don't understand it, that's fine. Feel free to come to theory track. This is a very, formal way of writing it. As long as you have a good grasp on the intuition of just, instead of doing momentum normally, we're doing momentum, but looking ahead a little bit, you should be good. So any other questions? Yes.
Actually, you go ahead.
Okay, yeah. So essentially, the reason why we're doing it less than one, right? It's probably easier to look at the momentum. Is we're essentially, imagine if alpha wasn't there, right? And we just were taking the cumulative sum over time, right? That's just a gradient that's just going to keep ballooning up forever, right? Like at each step, you're just going to add your current gradient to it, and then as time goes on, you're going to get a bigger and bigger gradient. That's not very useful, right? So the reason why we set it to a value less than 1, right, like 0.9 or 0.99, is to essentially have a form of exponential decay, right? Because if you think about it, at this current time, we are taking our current momentum and multiplying it by 0.9, right? So it's 90% of what it was before. And then the momentum before that is we took 90% of that, and 90% of 90% is all of a sudden 81%. And this is just a way for us to only really care about what's happening locally, right? We're just sort of decaying away. If our gradient has been, if we've accumulated a lot of momentum like in this direction, right, recently, we want that to show up a lot more than if we've had a lot of momentum in this direction, but like in the far past, right? So it's just a form of exponential decay. Yes. No, right? The gradient, so what we have up there, the V term is technically momentum, not velocity. And we aren't going to zero, right? Because the gradient, you know, we are always going to be updating, you know, well, we're dealing with matrices. And so what we get when we are doing this process, it's not going to zero, right? Because first of all, it doesn't make sense for something multidimensional to go to zero. It could make sense for it to go to like, you know, a matrix that's all zeros, but that is in practice like not really what is happening, right? We're taking the gradient at each location. That does not necessarily converge to a momentum of zero, right? We're subtracting it, yes, but you know, that's not, you know, decreasing it towards zero. That's just changing the momentum into the direction that makes slightly more sense, you know, like up here. So think about three possible situations. When alpha is 1, right? We just keep accumulating gradients forever. So if like all the way up here, right? Let me draw it out. Do we have a marker? Right. I don't know. If our last curve is like this, right? You know, and say we start right here. The gradient right here is in this direction, right? But say we take a bunch of gradient steps and we end up here. That was a really long time ago. We do not want this to be very impactful, right? We do not really care about what the gradient used to be. We only really care when we're talking about momentum. What's really relevant to us is what's like happened recently, right? Like in this region about. Does that make sense? And so because we're exponentially decaying it away, as we get further and further away from this point, it's going to matter less and less, right? So, but if it were the case that we're just 1, when we got to this point, this would still have as much impact as our gradient right here, right? Our gradient right here, right? It's going to be, when we look at this gradient right here, we're going to say, okay, it's telling us to go this way, but because alpha is 1, it's never decaying away. So this is just as relevant to our momentum. And so what we're going to see is we're just going to see an accumulation of all of it. That is not a good approach to gradient descent because we want, you know, this behavior to not be there. And then if you think about, if you had set it to a value that's like more than 1, all of a sudden what you're saying with that is that what's happening back here is more important than what's happening here, which makes even less sense, right? So does that make sense why we're choosing a value less than 1 to exponentially decay it away? A Nesterov momentum or?
It's right here. This?
Yes.
Yeah.
Exponential is 70 here.
Exponential. Yes.
I don't see, I'm not sure what the axes are.
Yeah, this, yes.
But
yeah, I think so.
Yeah. Yeah, I'm not entirely sure what the y-axis. I think it's loss.
Accuracy?
Or
it's probably
loss,
accuracy.
yeah.
I think it's accuracy. Yeah. Well, after well, they all kind of start out the same, but then they get worse.
Well, God, why don't we have any labels on here?
Yeah, it's we didn't label these very well.
These are great. Let's see. Yeah, so you do see it go away. I think the really important part here, though, is to understand why the like time-based and like constant are much more noisy than the step decay and exponential decay, right? Because when you look at it, it begins to flatten out towards the end, right? Which makes sense. As we decrease our learning rate, that means we're changing our model less and less. And so with like step decay and exponential decay, we are very quickly getting to a point where we aren't changing our model a ton, right? And so that means that it's, well, even if we do have small changes, right, they're not going to be huge and you're going to flatten out. Versus with like constant, right? No matter how far you get, you're always going to be updating by the same amount. So small noise is going to be like amplified, you know? And so, you know, what you'll see is this just helps promote towards the end, you know, just a form of like stability. So this isn't a learning rate, right? Learning rate refers to the epsilon right there, this E in front of the G, the E looking thing, right? And that's just some number that we multiply our gradient by, because, you know, when you have a gradient, it's relatively large numbers, right? And we don't want to be updating by the entire gradient, so we're just going to scale it down, you know? Or, I mean, you might want to scale it up, but like in general, you choose like a small number, so it scales the gradient down, because, you know, like we talk about,
Yeah.
if you were to be like here on like your loss landscape, you don't want to be taking like super huge steps, right? Like all the way down there, but you also don't want to be taking super tiny steps. You want to be taking, you know, decent sized steps. And so that's what the learning rate is deciding. It's deciding how big of a step you're taking. And momentum is just a way of us being like, hey, instead of looking at just the gradient where we are to inform how we should update, maybe we should look at like, you know, what's been happening recently. Because, you know, again, like if you had like an example like this, you know, if you were right here, your gradient would be like 0. You'd be like, okay, I'm at a local minimum. But clearly, we would ideally want to know like, hey, we've been going downhill a lot recently. Instead of stopping here, maybe we should continue going a little more. So. Well, it is depending on your learning rate, schedule it, right? So it, you know, like it can be constant, but it is just like a number. It's not like a learn parameter, if that's what you're asking.
I think it's, I'd say like, okay, basically it's a hyperparameter. So,
yeah.
So it's not like a thing that we learned during, like during the
you can essentially think of it as constant, yes. And then like if you're using a learning rate scheduler, it might be changing over time, but that change is, like Wade said, independent of the learn parameters. So I know that was a lot. If you have more questions about the calculus, we can talk more in person. But right now I want to see, are there any other questions about the content that we covered? All right. Yeah. That's everything. You know, you guys know where to find the notebooks. You know, if you have you know, the attendance code stuff, that's get good. Yeah, we'll be coming around.